cover was this theorem called the intermediate value theorem. So what I want to cover today is the intermediate value theorem, and I will usually refer to that as IVT. So what does it say? Well, let's let f be a continuous function on the closed and bounded interval from a to b. So it's a closed and bounded interval, so a and b are real numbers here. If w is any number between f of a and f of b, then f of c is equal to w for some c between a and b. So what this is saying is that you have this closed and bounded interval from a to b, right? Look at the value of f at a, value of f at b, so f of a and f of b. What this is telling you that if f is continuous, then f takes on any value between f of a and f of b. So let's say the value of f at a is 2, the value of f at b, let's say, is 5. What this is saying is that f takes on any value between 2 and 5. Am I making sense? Let me give you a picture. So if f takes on the value 2 and if f takes on the value 4, then f takes on any value between 2 and 4. That's what it is telling you, as long as f is continuous. So if you have a continuous function, if it takes the value 2 and the value 4, it's got to take any value between 2 and 4. So here's a graphical example. Let's say I have my x-axis here, my y-axis here. Okay, here's the origin right here. Let's say the number a is right here, and let's say the value of the function at a is f of a. So this height here is f of a. Okay, and the value of the function at b, let's say, is given by this height here, and that's the value of f of b. Is everybody okay? And let's say the graph of f looks like the following. Okay, that's the graph of f, let's say. So what this theorem is telling us, because f takes on the value f of a and it takes on the value f of b, it takes on any value in between f of a and f of b. So if w is any value, between f of a, if w is any value between f of a and f of b, then f takes on the value w at some c. So there is a value of c where c is between a and b, there is a value of C where f of C is W. So once again, look at the value of f at A at B, then f takes on any value in between, given that f is continuous from A to B. Is everybody okay? So there is some value C between A and B where the value of the function is exactly W. You can compare this example with the following example. Let's say now I have a function whose graph looks like the following. Let's say let's say the value of the function is exactly 1 when x is positive, and the value of the function is exactly negative 1 when x is negative. So that's how the graph looks like. Let's take this value. Let's say this is negative 2 here, and let's say this is positive 3 here. And I'm actually going to erase the other part here. So this is how the graph of this function looks like between negative 2 and 3. So notice that the function takes on the value negative 1, it takes on the value positive 1, right? But it doesn't take on any value between negative 1 and 1, right? F takes the value negative 1, it takes the value 1, but it doesn't take any value in between. Why? Notice that this function is discontinuous on that interval, right? Between negative 2 and 3, it is discontinuous at 0, right? So in this case, I cannot say that f takes on the value half, for example, right? It doesn't take on the value half. Is everybody okay? All right. So the intermediate value theorem doesn't apply to this function because it's discontinuous at 0. So here IVT doesn't apply. IVT can't be applied. Here's a specific case of the intermediate value theorem. Suppose that the value of the function at A is negative, the value of the function at B is positive, right? So f takes on a negative value, f takes on a positive value. By the intermediate value theorem, then I can say that f takes on the value 0, right? Because 0 is in between a negative and a positive. So if f takes on a negative value and a positive value, it's got to take on the value 0, given that the function is continuous. Okay, so that's what we're going to use in the next example. Let's say I have to show the equation x cubed minus x equals to 1 has a solution. Let's say I have to show that. How would I show that? Well, notice, the first thing that I'm going to do is I am going to rewrite the equation as this. So what I did is I put all the terms on the left-hand side, and the right-hand side is 0. And now I'm going to call the left-hand side to be the function f of x. So if I want to show that this equation has a solution, I basically have to show that the function f of x is 0 at some point c, right? Am I making sense? To show that this equation has a solution, I have to show that the function f takes on the value 0 at some number c. You agree with that? So how do I show that f takes on the value 0? That's the question then. Well, like I said, all I have to do is show that f takes on a negative value and f takes on a positive value somewhere, and then it's going to take on the value 0 by the intermediate value theorem. So can someone give me a value of x where f is negative? So give me a value of give me a value of x where f is negative. What's that? 0. Notice that f of 0 is negative 1, which is a negative number. Can you give me a value of f where f is positive? Sorry, give me a value of x where f is positive. Yeah, if I take x to be 2, you know what? Instead of taking 0 here, I am going to take 1, and still it's negative 1, and it's negative. And f of 2 would be 2 cubed minus 2 minus 1, which is what? 8 minus 3, which is 5, which is positive, right? So what do we have then? We have f of 1 is negative and f of 2 is positive, since f is a polynomial function, right? So since f of x is continuous on 1 to 2, right? In fact, this function is continuous everywhere, but in particular it's continuous between 1 and 2 by intermediate value theorem. F of c is 0 for some c where? For some c. So what we said is the value of f at 1 is negative, at 2 it's positive, so it's got to take on the value 0 where? Well, what's the location of c? Between 1 and 2. So there is a value of c between 1 and 2 where f is 0. So basically then the equation that we started with, it has a solution between 1 and 2. So the equation that we started with has a solution c between 1 and 2. So it has a solution c between 1 and 2. So not only we showed there is a solution, but we also showed that the approximate location of the solution is between 1 and 2. Is that okay? Is everybody doing okay? Okay. One way. Let's do another example like this before we move on. Let's say show cosine x equals to x has a solution. So I want to show this equation has a solution. Once again, the first step is you want to put all the terms on the left hand side and then call the left hand side to be f of x. Is f of x continuous? Notice that f of x is continuous everywhere, right? Because cosine is continuous everywhere, x is continuous everywhere, right? So can someone now give me a value of f where f is negative? And give me a value of f where f is positive. What is f of 0? F of 0 would be cosine of 0 minus 0, right? What is cosine 0? 1. So this is 1, and that's positive. Okay. Can you give me a value of x where this quantity would be negative? Good, very good. So pi over 2, I get cosine pi over 2 minus pi over 2, which is the same cosine of 90 degree is 0. So this is negative pi over 2, which is less than 0. So what we have obtained is that f of 0 is positive, and f of negative f of pi over 2 is negative. Now f is clearly, remember, f of x is cosine x minus x. It is clearly continuous on 0 to pi over 2. In fact, it's continuous everywhere, like we said. But in particular, it's continuous there. So, by intermediate value theorem, f of c is 0 for some c where? For some c between 0 and pi over 2. Okay? So because f takes on a negative value and a positive value, being a continuous function, it's got to take on any value in between, so it takes on the value 0. And so that implies that our equation does the equation cosine x equals to x has a solution c, where c is between 0 and pi over 2. So we also know the approximate location of that solution. If you think about the cosine function, right? Think about the cosine function graph. If you know the graph of the cosine function, this equation, what's the solution of this equation? Is the intersection of the graph of cosine and the graph of x, right? And the graph of x is a line, right? So graphically, think about the if you think about it, it makes sense. The solution is between 0 and pi over 2. Is everybody okay? This guy has another. Should this have another solution? No. The cosine starts at 1, right? So it looks like 1, and then it looks like this. So if you look at it, when you make that line, it doesn't cross anywhere else. Okay. Okay, so that's that. Once again, so the intermediate value theorem says if f is a continuous function, then f takes on any value between f of a and f of b for any a and b. So if f is continuous between a and b, then f takes on any value between f of a and f of b. One nice way to think about it is that think about f is the speed function as you go from Ada to Columbus. So Friday night you're going from Ada to Columbus by driving, and f is your speed function, right? So usually you started out as being a good driver. You are driving at some point, let's say at time A you're driving at 60 miles per hour. That's your speed at time A. At another time you are tired and cranky, you are driving at 90 miles per hour. So at time B you drive at 90 miles per hour, at time A you drive at 60 miles per hour, right? As you are driving, you're continuously driving, so your speed function is a continuous function. So because your speed at some point was 60 miles per hour and some point it was 90 miles per hour, I can say that your speed must have been 80 miles per hour at some point. Am I making sense? So your speed function, your speed at time A is 60, at time B it is 90. So your speed function will take on any value between 60 and 90. Is that making sense? So that's one way you can think about this IVT. Okay, so that's the end of section 1.8. Once again, your quiz on Friday will be on this section. Okay. Okay, so now we are going to move into chapter 2, and what I'm going to do though is I think I'm going to use a new page because my other page is too big now, and at some point it might crash. So we are going to look at chapter 2 now. So remember when I started talking about functions, we looked at functions in applications areas like the position function as a function of time, velocity as a function of time, speed as a function of time, acceleration as a function of time. In economics, demand as a function of demand for a commodity as a function of price, supply of a commodity as a function of price, population as a function of time, of a bacteria growth maybe, population growth, and so on. Many other functions are there. So you have lots of quantities that you're interested in, and you also are interested in the relationship among those quantities. And also, if you think about the position function, okay, it's an interesting function, but even more interesting is to talk about its rate, right? What's the rate of change of the position function? So one way you study the relationship between time and position is by studying the rate of change of position with respect to time. What is that? Well, that's just velocity, right? Velocity is the rate of change of position. What is acceleration? That's the rate of change of velocity, right? So the rate of change of a function is a quantity that we usually study to study the function. If you think about the demand of a commodity as or a supply of a commodity as a function of price, think about the rate of supply function. Again, supply of a commodity means at a given price, what quantity of a commodity is supplied in the market by manufacturers. So that's the supply function. So what's the rate of change of that supply function as a function of price? What it's going to tell you, the rate, is going to tell you if you increase the price by 1 unit. Let's think about tomatoes. If you increase the tomato price by $1, right, how much will the farmers be willing to supply more and grow more? Am I making sense? So if you increase the price by $1 or 1 unit of currency, how much will the tomato growers be willing to supply to the market? Okay, so that's the rate of change of supply as a function of price. Tax rate. If you increase income by 1 unit, maybe 1 unit means $1,000 or $10,000. If you increase your income by 1 unit, how much will your tax rate increase, right? How much will your tax increase? So that's the tax rate. Is everybody okay? So my point is, we are interested in rates of functions, and not only just the average rate. We are interested in the instantaneous rate. Okay. So let's go back to one of the examples that we did with a bug moving along a straight line. So let's suppose you have a bug, and the bug is moving along a straight line. 0 is the reference point. At time t, the position of the bug is given by, let's say, P of t. So P of t gives you the position at time t. Let's pick a specific time A, and at that time, let's say this is the position of the bug. And so what's the average velocity of the bug over the interval from A to t? Well, it's the net displacement, which is the change in position. So what's the change in position? P of t minus P of A, that's the change in position, which we call net displacement in physics. And then if I divide it by the length of time, which is what? T minus A, I get the average velocity, right? But then if I take the limit as t goes to A, it means that I am shrinking the period toward A. And if I look at this limit, whatever that limit is, that's the instantaneous velocity. Am I making sense? So you look at the average velocity from time A to t, and then you allow t to go to A. Look at what's happening to the ratio, and the ratio approaches a number, and that number is the instantaneous velocity at A. So this is the instantaneous velocity at time A. Instantaneous velocity at time A. So what are we doing to find the instantaneous velocity? We look at the average velocity and we take the limit, right? It's the change in, so this quantity that I have here, what is that? It's the change in position divided by change in time, right? Change in time. So this is giving me the rate of change of position with respect to change in time. The rate of change of position with respect to change in time. Is everybody okay? So this is giving me the rate of change of position with respect to change in time. But this is position function isn't the only one for which we want to know the instantaneous rate. There are many other functions, so we need to talk about it in a general way. So let's what we call this limit? We call this limit to be the derivative of the position function at time A. The derivative of the position function at time A is given by that limit, and the derivative of the position function is the velocity function. So generally, if I have any function, what's the derivative of that function? What's the instantaneous rate of change of that function at A? So the derivative of a function f at some number A is given by f prime of A. So it's denoted by f prime of A, and the derivative at A is given by the limit as x goes to A of f of x minus f of A divided by x minus A. So it's the change in f value divided by the change in input value. So that's the derivative of a function at some number A, and this is the instantaneous rate of change of f at A. This is the instantaneous rate of change of f at A. Of course, this is provided the limit exists, right? Provided So the derivative at A is defined by this limit, provided the limit exists. Provided the limit exists. There are some language that we use in this regard. We say f is differentiable at A if f prime of A exists, and we say, meaning that f prime of A exists means that that limit exists. We say that f is not differentiable. F is not differentiable at A if f prime of A does not exist. Let's look at a couple of examples to explain how this limit works. Here is an example. Did you guys need time to write that up? Everybody has that down? Okay, so here's an example. Let's take the function f of x to be given by x squared, and what I want to know is what is f prime of, let's say, 2. So what's the derivative of the function at 2? Well, by definition, what is that? It's the limit as x goes to what? 2. F of x minus f of 2 divided by x minus 2. Okay, so what is that limit? This is the limit as x goes to 2. What is f of x? X squared. What is f of 2? 4. So we get this. What's the limit of this? If I plug in 2 for x, I get 0 divided by 0. And if I have 0 divided by 0, I factor out, right? So this would be the limit as x going to 2. What is that? X minus 2 times x plus 2 over x minus 2. Cancel out x minus 2. And the limit is what? When you plug in 2 now, you get 4, right? Is everybody okay? Okay, so what we have found in this case then, that f prime of 2 is 4. Okay, so that's how we can find the derivative of the function at a given number like 2. There is another way of writing the derivative. We define the derivative at A as a limit, and there is another way of writing that limit. So what is that? And that's sometimes useful. So here's the remark. If we define the derivative of f at A by this limit, and is the limit of f of x minus f of A divided by x minus A. This is known as a difference quotient. You guys have computed this quantities in the algebra review. This is called the ratio that I have here is called the difference quotient of f at A. And this limit is in fact the same as the limit as h goes to 0, okay, of f of x, f of a plus h minus f of a divided by h. So these two limits are in fact the same. How? Let's see. So I am going to start with the left hand side, okay? And in the left hand side I am going to plug in x equals to x minus a equals to h, okay? So here's the left hand side is x minus a f of x minus f of a over x minus a. So what I'm going to do here is I am going to set h to be x minus a. If I set h to be x minus a, what do I get? Well, the denominator is just h, right? So if I take h to be x minus a, then what is x in terms of h? If h is x minus a, I can solve for x, right? If I solve for x, I'll get what? I'll get x to be, x will be a plus h, right? And minus f of a. So this quantity, this ratio looks like this when I write it in terms of h. Now how about the limit as x goes to a? Well, notice if x approaches a, right, then x minus a goes to 0. So h goes to 0. If x goes to a, h goes to 0. On the other hand, if h goes to 0, then x minus a goes to 0, which means x is going to a. So x goes to a if and only if h goes to 0. And so these two limits are going to be the same. Okay? So these two limits are the same. So then I can say that the derivative of f at a is also equal to the limit as h goes to 0 of f of a plus h minus f of a divided by h. Let's do an example of computing the derivative by using this limit. So let's say this time I have the function f of x equals to root x. And let's say I want to find the derivative of f at, let's not take 2 because root of 2 is not nice. So let's take root of 9. F prime of 9. So what is f prime of 9? If it will be, by definition, it would be the limit as h goes to 0 of f of what? 9 plus h minus f of 9 divided by h. Okay? And okay, so what is f of 9 plus h? F of 9 plus h would be the root of 9 plus h, right? And f of 9 is what? F of 9 would be 3. Root of 9 is 3. Divided by h. Okay, if I plug in a 0 for h, what do I get? I get 0 divided by 0. And so I have to sort of try to get rid of h then, right? And how do I get rid of h? I rationalize. This problem, did it appear in your exam? This is one of the limit problems in the exam. So how did you do that? Well, you rationalized. And so to rationalize, we take the limit as h goes to 0. Let me write actually here. We multiply by root of 9 plus h plus 3 divided by the root of 9 plus h plus 3. And if we do that, what am I going to get in the numerator? It will be h times the root of 9 plus h plus 3. In the numerator, when I multiply out, what do I get? I'm going to get the square of this guy minus the square of this guy, right? Just FOIL it, simplify it, you'll see that you get the square of this minus the square of that. What is that? What is the square of 9 plus h? 9 plus h. What's the square of 3? So you get this. So what's going to happen? 9 and 9 cancels out. And once you cancel them out, you can also cancel out h's, right? So altogether then, what you have is the limit as h goes to 0 of 1 over. And then if you now plug in 0 for h, what do you get? You get 1/6. So what we have found then is the derivative of the function at 9 is 1/6. Is everybody okay? Yeah.
Could you just find the derivatives for the accident?
Okay. If you are anxious about using formulas, it's going to come pretty soon. But right now, in section 2.1 and 2.2, you have to compute the derivatives in this way. The first in the second most important event that's coming up in this course, the first question will be, I'll give you a function and ask you what's the derivative of the function at 2, and you have to do it by using the limit definition. So that will be the first problem. And in section 2.1 and 2.2, you have to wait, and then from 2.3 on, you can use all the formulas you want, okay?